All right, a video transcoding system with real-time logs. The first question, what is video transcoding? So, in simple words, whenever a video is uploaded onto a streaming platform, whether it's YouTube, Netflix, Amazon Prime, Hulu, Disney, Hotstar, whatever it is, one of the most common things that happens across these platforms is that this video is converted into different bit rates. What does different bit rates mean? Different bit rates essentially refers to the different qualities you can watch the video in. So 1080p, 720p, 360p, and 480p, and whatever else, 2160 or 1440, whatever it is. And whenever you upload a video onto, let's say, YouTube, this video is transcoded, aka converted into each of these different qualities as separate video files. Now, this differs per platform how this happens, but video transcoding is essentially the process of converting a given input video into these different qualities. And on a platform like YouTube, whenever you upload a video, the underlying mechanism that would technically happen is this video that you're uploading would get converted to these different qualities, which can then be viewed by the end user when they're watching the video. And the point of this is, let's say I have a bad internet connection, I want to be able to watch it in 360p. If I have a good internet connection, I want to just be able to watch it in 1080p. And that's basically the use case. Now, as for why this is a problem statement and why this is deserved to be discussed. So theoretically, a video can very simply be transcoded using a very popular tool library that is called FFmpeg. And FFmpeg has commands that you can run essentially within your terminal where you give it an input file. So this is an input MP4 file, and it would convert it into the desired bitrate. And running this command is fairly simple, right? Doing it via the CLI for a single video is extremely simple, and you can do it on your own machine. However, it gets tricky when a platform like YouTube has thousands of millions of videos being uploaded per second, and all of these videos need to be transcoded. So, if we go into the crux of the problem, essentially there are a couple of things to consider. Firstly, the fact that this process is computationally expensive. Now, because we're converting a video into a different bitrate, this is computationally expensive and this is a long operation, which means that this will not just be like a 1 second thing or a 2 second thing or a 10 second thing. This process could potentially take minutes, especially because you're trying to convert it into different bit rates. So this process could theoretically take minutes. And it could differ by the length of the video or the current quality of the video or a bunch of other parameters, really. And therefore this is a long running operation, and we need to figure out a way such that we can support this long running operation, because in the CLI, it's fairly simple to be able to do it. However, it gets complicated as millions of videos are being uploaded at the same time. And the third point here is that one video's transcoding should not affect the other. What does that mean? That essentially means that, let's say I have uploaded a video and let's say another person has uploaded a video onto YouTube. If my video is being transcoded and let's say my video, for some reason something crashes, something errors out while my video is being transcoded, their process should not be affected. It needs to be multi-tenant in nature, such that my video processes should not affect his or her video processes, essentially. All right. I'll first talk about the initial naive solution. And when I say naive, I just mean that the solution ultimately won't work. And I'll talk about why the solution is not great and firstly what the solution is, of course. So let's say we need to transcode videos, right? And the first step in the process is, given we have a video file with us, let's say we have an MP4 file that is, let's say, stored on a cloud storage like S3. We don't need to figure out like that entire part, but like of how it's reaching S3 and stuff like that. But let's just assume we have a video that is stored in S3, and we have an S3 URL, which is the URL to the actual video. So when the video is stored in an object storage like AWS S3, we get a URL that is returned, and the URL is essentially a link to the video. Now, this is also assuming this is a bad architecture, but we're assuming here that the video is publicly available on a URL, the video itself. So essentially, let's say given we have the video URL, that's our baseline assumption for now, and we don't need to think about how the video URL, how we're getting the actual video URL. We need to figure out to transcode the video. Now, obviously, as we talked about earlier, the one thing that we can just do is run this ffmpeg command across four different bit rates that we want to convert to, and that would work, right? That would give us different video files and different video files for the same video in different qualities. Now, let's think about the practical implementation of when we have 1,000 videos that are being uploaded. So let's say we have, this is, let's say, the YouTube's backend server, right? And we have a bunch of videos coming in, a bunch of video requests, transcode video, transcode video, transcode video, and we need to transcode each of these videos. So the sort of first intuitive solution, which says run on traditional backend servers, could just be that given that this is the YouTube server, we actually just run all the transcoding processes here. So essentially, we run all of the FFmpeg commands here itself on the YouTube servers. So which means that let's say we have 4 or 5 different videos coming in, we just run it on YouTube servers and videos are transcoded. We get the different bit rates that we're essentially looking for, and then we figure out what to do there from next, right? We don't care about the next part, but the point is we need to transcode videos, and the first solution can just be let's do it on YouTube servers itself. And that brings in the first question. Each of these YouTube servers, they're obviously just machines that are running in the cloud, right? They're like any other laptop machine that you can almost think, like any other laptop almost that you can think of. They're not actually laptops, but you can think of them as laptops, right? Which have their own set of RAM, their own CPU, and their own set of allocated resources. And let's say if I were to run these on YouTube servers, each of them, obviously, as I said, have their own set of CPU and RAM, and eventually it would run out of it, because as we said earlier, transcoding is a computationally expensive process, which means that we can't just feed 1,000 videos to be transcoded on a single YouTube server, right? We need to possibly have another YouTube server. So, the naive thing that we can think of, or the first thing we can think of, is let's send our next set of requests to another YouTube server, right? Now, if we look here, just at this ugly diagram that we have here, the one thing that we're automatically noticing is that multiple processes are going to the same YouTube server and getting transcoded. What does that mean? It means, if we look at the third point here, we need to manage concurrent processes. This means that if any of these transcoding processes fail midway for some reason, we need to figure out a way for we need to manage essentially a bunch of these running processes together and send back the response to the UI or wherever else this response needs to go to, saying that this specific process errored due to this XYZ reason. And also, the other problem is that, oh, no, oh, here it is. I lost my diagram for a second. So essentially, we see here that we need to manage a bunch of these processes together, right? And there is one big problem here, which is that if one process goes down, there is a chance that it could actually affect the other processes. For example, if one process goes down because, let's say, it consumes too much memory, right? Like, let's say one of these videos is significantly larger than the other videos. If this process causes this server to go down because it's consuming too much memory, all of the other processes go down too. And we also need to manage all of these concurrent processes together, which means that if one errors, we need to make sure that one specific errors for that one specific video is propagated back to wherever it needs to go to, and the error is actually visible, let's say on whatever layer it is. If it's in the UI, where the UI is something like this, where you actually see it in logs or whatever it is, right? And this is complex because we're managing multiple different processes at the same time. And each of these processes are not interlinked at all. They're actually not even a part of the same global process. Where, let's say, if these were 5 different videos of the same user, sure, maybe, right? But they're not. They're 5 different videos of completely different people. And managing all of them together would be a nightmare. And if one fails due to any memory or CPU constraints, or if the server goes down, everything just fails. And a, a user who has let's say like a 5 second video, for example, that's being transcoded, could also be affected by this, just because there was another, let's say, Mr. Beast video which is an hour long, was which took too much memory out of this specific server or whatever, so to speak. So this is a problem. And the second last point here, message queue connection failure handling, we can ignore that, and I'll come to why that's applicable, but we can ignore that for now. But essentially, manually handling failures. So if one process fails, what happens? How do you propagate the error back? And it's complex, and it's also not ideal, because especially because of one instance going down can cause several processes to go down. So this doesn't work. And again, the auto scale issue as well exists here, where, for example, if you have 4 or 5 different processes that are running, right, and let's say 6 processes coming in on this specific YouTube server, let's say we only have, let's say, 1 GB of RAM left, because everything else is being consumed by the other processes. Well, that may not be enough for the incoming video, which means that it needs to go to another server. Now there's extra network traffic that you're creating, and that is actually might not even how the architecture would work. So it's pointless. It becomes extremely complicated, and we'll have to find extremely hacky ways to even make this work, which is not great. And we need something cleaner, and we need more process isolation, such that if one transcoding process fails, it shouldn't affect the other, so on and so forth. Now, talking of the better solution, and from our previous conversation, like, the most important aspect here is to figure out a way for each of these processes that we have here for transcoding videos to be isolated from each other. And we need to figure out a way that all of these processes aren't tightly coupled, and there's an easier way for us to be able to track each process that it's running, if that process errors out, and then sending back error logs, or basically whatever else we need to do. And let's forget what AWS ECS is. Let's just think from first principles. So we need a way for each of these incoming processes to come in and to run separately, and to essentially not intertwine itself with other transcoding jobs. The most intuitive thing that works for something like this is, and where we require process isolation, is to actually run this in a container. Now, when I say container, I specifically refer to possibly running this within a Docker container. And the idea is that each of these processes takes is its own little small machine where it ends up running. And let's say if something fails here, this process goes down, but these still remain alive. If something fails here, this process goes down, but these remain alive. And just because this is, let's say, a 5 second video versus this is, let's say, a 2 hour video, this process is not going to get affected at all, because this has its own container it's actually running in. And specifically, the container technology that I'm referring here to is Docker, where, we can essentially wrap these around in Docker containers, each of these processes in Docker containers, and we can just run these ffmpeg commands that we talked about in Docker containers, which gives us this process isolation. And we no more need to have problems like, for example, how do you auto scale multiple processes running, because each of these just belong to their own set of own containers, and you can just spin up more containers. And there is no managing of concurrent processes because each of these is a separate process and each process is managed independently. There is no intertwining. And also failure handling, right? If one process fails, it is that specific process that fails and nothing else, right? And this is now great because we're now only managing per single process, and a single process cannot affect the other processes. And if this container goes down for some reason, the other containers won't. And this is a great solution. Now, in terms of actual application architecture, right? Like now we said that sure we can use Docker, but one of the things that AWS provides to be able to do use cases like this is ECS. ECS basically stands for AWS's Elastic Container Service. So if we go back here, this is essentially Amazon Elastic Container Service. And the whole point here is that you can define certain tasks or task definitions essentially. And these tasks would run independently of each other whenever you create them. So theoretically, if we go here, if we see here, right, within our own Elastic Container Service cluster, we have no tasks running, right? But when you actually spin up, let's say, a new transcoding task, we actually spin up a new task, right? And you can go into this task and you can do whatever you want with this task. And this task is basically just a Docker file, right? And all that Docker file is doing is basically just running these commands. Long story short, right? The whole point is to be able to run these ffmpeg commands independently in different Docker containers so that one process doesn't affect the other, right? And if we go here, so some of the benefits, right? Firstly, obviously, one task is one video job, which I talked about. There's no shared memory, there's no process conflicts because everything is independent, everything is a new task. Secondly, failed container impacts only one job. We talked about this earlier, where there's very high level of isolation now. And thirdly, again, if a task fails, right, if a certain task fails, you can essentially just restart that task based on health checks you can create. So let's say we have the YouTube server, right? So let's say this is our YouTube server, which, let's say, within AWS starts this task, right? And let's say we do one more of this. It starts this second task, right? And maybe what we could do is that if this task fails, right, based on health checks that we might be doing here, if this specific task fails, we can basically restart this task all over again, right? And again, now this process is not affected and the other processes that might be running may actually not get affected. And finish tasks shut down cleanly. So this is also obviously great because it's essentially a Docker file, and Docker file has just a set of steps that would eventually end at some point, after which the task shutting down is managed by AWS itself, which is extremely clean because now we've outsourced that. And also ECS integrates with CloudWatch. So if we go into what CloudWatch is, CloudWatch is basically a monitoring platform. And the point is that what CloudWatch allows you to do is that it allows you to monitor certain behaviors and tasks. So if we go here, the whole point is that you can track different metrics for certain processes slash tasks that are running. So the whole point is that you can actually track every job's or every task's performance when it's running, for how long it's taking, and possibly even logs. And that would mostly be done through CloudTrail, actually, which is where you would see logs for task creation and things of that nature. But the point is that you can track job level performance based on CloudWatch, right? Which can act as your monitoring solution, basically. And that's a really big advantage of using something like AWS Elastic Container Service because, as I said earlier, it's all isolated and it's all extremely multi-tenant in nature, basically, where nothing affects on the other job that's running.